morning, students. I welcome you all for another session of the some module, that is deflection of beams. Okay, so in the previous session we have studied the two important theorems. One is Moore's theorem 1, and second one is Moore's theorem 2. So Moore's theorem 1 is used to find out the slope at various points on the beam, and Moore's theorem 2 is used to find out the deflection at various points on the beam. So let us take a standard cases, that is first we'll consider the simply supported beam, okay, and with a single point load, and try to find out slope and deflection at various points. Okay, so the heading what we're going to study here is slope and deflection for standard loading cases for beams using moment area method. So now we're going to concentrate only on this moment area method. So using this moment area method, we're going to find out slope and deflection at various points on the beams. So first let us consider simply supported beam. Okay, in that slope and deflection of a simply supported beam carrying point load at the center. Now see, whatever you are seeing capital W, it is the point load which is acting at the center of simply supported beam, that is A and B are two simple supports. Okay, so the load will be acting at center. So the total span of the beam, this simply supported beam, is L. So capital L will be the total span of the beam. Okay, then half will be L by 2, and this is L by 2. Okay, so since the load is at the center, okay, now first try to find out the reactions. Okay, so since it is a simple support, there is one reaction, that is RA, and this is also simple support, means another reaction RB. So first we'll find out RA and RB. As you know, the load is exactly at the center. Okay, the total load is W. So then since it is a symmetrical loading, half of this load will be reaction RA, half of this total load will be reaction RB. So therefore reaction RA is equal to this W by 2, and reaction this RB is equal to W by 2. Okay, so since the load is symmetrical, or the load is at the center, reaction RA and RB will be total load divided by 2. So both are same. Now let us consider this. Okay, as I have told, this reaction RA is equal to W by 2, RB is equal to W by 2. Now calculate the bending moment now. Okay, so in previous semester also you studied already how to calculate the bending moment. Okay, so let us calculate the bending moment at A, bending moment at C, and bending moment at B with this loading condition. Now we know reaction RA W by 2, reaction RB is W by 2, this load W at point C. So let us calculate bending moment at A, B and C. So first bending moment at A. So now calculate the bending moment at A. So bending moment at A is equal to what? RA into perpendicular distance. So what is the perpendicular distance between RA and A? So since it is RA is passing through A only, the bending moment at A will be 0. So bending moment at A will be 0. Similarly, bending moment at B. So bending moment at B will be again 0. That is RB into perpendicular distance is 0. So the bending moment at B is also 0. Now let us calculate bending moment at C. So bending moment at C, that is indicating MC. So bending moment at C, MC is equal to, so there are two options. Either you can consider half portion from this end, that is you can consider portion AC, or you can consider portion BC. Okay, from any one side you can calculate considering only half span of the beam. So let us consider this portion AC. Okay, so what is the bending moment at C now? First take this RA. Okay, so RA into what is the distance between RA and C? It is L by 2. Now see, RA into L by 2. Okay, so it is plus. Why is this plus? Now see, because of this reaction. Okay, because of this reaction, how this portion AC bends now? This portion AC bends like this. So because of this, if you push this okay upward, the bending will be like this. AC will be like this. So this goes up. So AC will be like this. Means it will be sagging. Okay, so this portion will going to sag. So sagging means plus. So the bending moment at C is equal to plus Ra into L by 2. Again, if you consider this load, so what is bending moment due to this load now? W into 0. So since it is passing through C only, the bending moment due to this W is 0. So only it is plus Ra into L by 2. So plus Ra into L by 2. So that is equal to Ra, already it is known, W by 2. So plus Ra is W by 2 into L by 2. So the total bending moment at C is equal to W L by 4. So capital W into L by 4. So this is the bending moment at C. So bending moment at A is 0. Bending moment at B is 0. So bending moment at C is plus WL by 4. Now draw these ordinates in the form of bending moment diagram. So first draw the baseline, that is beam A, C, B. So beam A, C, B. Now mark the bending moment. So what is bending moment at A? It is 0. So bending moment at A is 0. Bending moment at B is 0. And bending moment at C is plus WL by 4. Plus means above the baseline you will going to mark. So bending moment at C is WL by 4 plus. Okay. Now join. Now here to here no UDL is there. Here also no UDL is there. Only W is there. And we have calculated WL by 4 bending moment. So complete this. Here it is 0. Here it is WL by 4. Here it is again 0. So the bending moment diagram will be triangle. Bending moment diagram will be triangle, and maximum bending moment will be at the center, that is WL by 4, because of the point load at the center. So this is bending moment diagram. Now see here. So this portion is L by 2 and this length will be L by 2. So the total span is L. So this is L by 2. This is L by 2. Okay. So next, now try to understand here. One more dotted line I have drawn here. Okay, so this dotted line indicates bending shape of the beam. Now when this load comes on the, okay, when the load comes on this beam at point C, okay, the deflection, so here the deflection will be 0 because of support. The beam will not going to deflect here. The beam here also, because of support, the beam will not going to deflect here. But because of this point load downward, the beam will going to bend like this, A, and this is B, and this is the deflection, not bending moment. I am not talking about bending moment. This is a deflection. So because of this central load, it will going to come down. So due to this load, the bending action of this beam will be A, C, B. Okay, this is the bending action of the beam, or deflected shape of the beam, what you can say. So here deflection is 0. Here deflection is 0. Here deflection is maximum. Okay. Here deflection will be maximum. Now another important thing is, first we'll find out the slope. Now remember, for simply supported beam, whatever may be the load, at two simple supports, slope will be there, but deflection will be 0. No deflection, but slope will be there. Means slope at A is there. If you draw the tangent here, okay, this is the slope. This is theta A. Similarly, if you draw the tangent here, touching this curve, so this is angle made by this tangent will be theta B. That is slope at B, slope at A. Means remember, for simply supported beam, at two simple support, slope will be there, but deflection will be 0. Okay, so this is the case of what? Symmetrical loading. Hence slope is 0 at the center. Now see, if you draw a tangent at this point, tangent will be like this now. So there will be no angle. Okay, the slope will be 0 at center. So slope will be 0 at center, but slope is there at A, slope is there at B. Okay, so this is the case of symmetrical loading. Hence slope is 0 at the center, that is at point C, but the deflection is maximum at the center. Now see, for this beam, theta A is there, theta B is there, but deflection at A, that is YA is 0, YB is 0, but YC is there. Here slope is 0, but deflection is there. Okay, so that we're going to find out now. Okay, now whatever we have derived the two equations, two theorems, okay, we're going to use those two theorems. What is first theorem? So Moore's first theorem for slope. So using first theorem, we're going to get the slope. So what that Moore's first theorem indicates? Now I want slope at A. Okay, so similar, see, since theta A and theta B are same here. Why? This is a symmetrical loading. Okay, so theta A, theta B are same. So you can consider any one. Okay, right. So slope at A is equal to what this theorem states? Area of bending moment diagram between A and C divided by EI. So area of bending moment diagram between 2 points divided by EI. Now since it is a symmetrical loading, we are going to consider only half portion of the bending moment diagram. This is bending moment diagram now. I want slope at A. Okay, I want slope at A. So that is theta A. So theta A is equal to what? You have to consider area of bending moment diagram between A and C. Half portion. So area of bending moment diagram between A. Slope means you have to find out the area. Okay, slope means you have to find out the area. So now what is the area between A and C now? What is the area between A and C? See this, okay, dashed portion. So this is point A, this is point C. So this is the area. So if you take this area divided by EI, will give slope at A, that is theta A. Now see, slope at A, theta A is equal to area of bending moment diagram between A and C divided by EI. First calculate this, what is area of bending moment diagram between A and C. Okay, so area of bending moment diagram between A and C is, so area A is equal to, what is the area? This is a triangle, half base into height. Okay, so this is a triangle, area between A and C is the triangle. So what is the area of triangle? Half base into height. Half, what is base now? Base is what? L by 2. Okay, base is L by 2. What is height? WL by 4. Bending moment already you have calculated this point. So height will be WL by 4. So base will be L by 2. So area of this triangle between A and C is what? Half, base is L by 2, height is WL by 4. So half, base is L by 2, height is WL by 4. So therefore area between A and C is what? W, okay, W L into this L, WL square divided by, okay, 16. See, 4 into 2 into 2. So WL square by 16. This is the area between A and C, area of bending moment diagram between A and C. So now substitute here. So what is slope at A now? Theta A is equal to, okay, so area is WL square by 16, okay, WL square by 16 divided by EI. So divided by EI, WL square by 16 EI. Okay, so this is the slope at A, that is theta A. So since the load is symmetrical, theta B is also same. So similarly, slope at B is equal to theta B, that is WL square by 16 EI. So slope at A and slope at B are same, it is WL square by 16 EI. Okay, so using this Moore's first theorem, we are going to calculate the, okay, slope at the various points. Now next, second theorem we are going to use. Second theorem, what second theorem we are going to give? Second theorem we are going to use to get the deflection at various points. Deflection at various points. Now see, where is the deflection now? See this, don't see this now. Okay, see this deflected curve, deflected curve. So is there any deflection here? The point A will be here only, or support will be here only. So deflection at A is 0, deflection at B is 0, but the point C will come here. Because of this load, the point C will come here. So this is the deflection at C. So deflection means we are going to indicate y. So y a is 0, y b is 0, but maximum deflection is at the center, that is yc. Now we are going to calculate yc. So what the most second theorem states, deflection is equal to, that is y is equal to a into x bar divided by ei. So remember, a into x bar divided by ei. So whatever the a we have calculated here, this is the area now, area divided by ei, same a divided by ei multiply x bar, okay, multiply x bar. So what is a? Again, as it is, a will be, now see, I want to calculate a deflection at C now, deflection at C, point C. Okay, here deflection is 0. So you can consider again area between A and C. Area between A and C, bending moment area. So what is area between A and C? This is the area. Okay, this triangle is the area between A and C, because here deflection at A is 0, but deflection we want C. Or even you can consider this also, BC portion also. Deflection at B is 0, deflection at C will be YC. Half portion you can consider this, or half portion of this B. Okay. Now what is this terms in this equation? Area. Capital A is area of bending moment diagram between A and C. Area of bending moment diagram between A and C. And already we have calculated, this is area is equal to WL square by 16. Okay. Already we have calculated area between A and C is WL square by 16. WL square by 16. Then what is X bar? What is X bar? X bar is nothing but distance of CG. Okay. Distance of centroid or center of gravity of the area from A, support A. Now see, this is area now. Okay, now there is a centroid here. There is a centroid here. Okay, so we know that already the centroid of triangle, the centroid of the triangle will be calculated like this. So if you consider from this end, from A, it is how much? It is 2/3 of base. 2/3 of base. Okay. From C, it is how much? From C, it is 1/3 of base. Okay, already you have studied this. So if you, this is a 0 intensity. Okay, from 0 intensity, okay, the centroid will be at a distance of 2/3 of base L by 2. So from here it is 2/3 of L by 2. From here it is 1/3 of L by 2. Okay, but now what we're going to consider? We're going to consider the distance from A, centroid from A, because here deflection is 0. Okay, so this is a reference point, deflection is 0. We want deflection at C, means we have to take the centroid distance from A to this point. So area we know, then multiply x bar. This is the x bar. From here it is 2/3 of L by 2 base. 2/3 of base, it is L by 2. Therefore, so x bar is 2/3 into L by 2. Okay, that is L by, okay, this two get cancelled, this is L by 3. So x bar is L by 3. So therefore deflection at C now, deflection at the center, that is below the point load. So deflection at C, that is the maximum deflection. So y max is equal to, so here y indicates deflection, theta indicates slope. Remember, slope means theta, deflection means y. So it is at C, it is maximum. So it is y max is equal to, so substitute in this formula, A into x bar. Okay, so what is A? What is A? Area already calculated, it is WL square by 16. WL square by 16 into x bar. X bar is L by 3. Okay, WL square by 16 into x bar is L by 3, whole divided by EI. Okay, whole divided by EI. So it is W L square into L, that is W L cube. Okay, W L square into L, it is WL cube, divided by 16 into 3, 48. Okay, divided by 16 into 3, it is 48. This EI goes up here, so 48 EI. So WL cube divided by 48 EI will be the deflection at center, that is at point C. Okay, deflection at A is 0. Okay, now see what it means. So when this load comes at the center W, the beam will going to deflect like this, or it will going to bend like this. So there is no deflection, that is YA is 0, YB is 0, and this YC. How much this deflection? Deflection at C will be WL cube divided by 48 EI. Suppose if you want to, if you take this load W is equal to 20 kilonewton. Okay, W is equal to 20 kilonewton. So then RA will be how much? 20 divided by 2. RB will be 20 divided by 2. And as per the derivation, what is the maximum deflection at the center now? WL cube divided by 48 EI. So if you substitute W is equal to 20 kilonewton, L span you can substitute, EI also you can consider moment of I is moment of inertia, E is the Young's modulus of elasticity. If these two values are given, then you can calculate the deflection. But now in this case you can keep EI as it is. So the deflection at center is equal to WL cube divided by 48 EI. Now see, last you can write down the final things what you have calculated. Slope at A, theta A, this is WL square divided by 16 EI. WL square divided by 16 EI. Theta B is also same, WL square divided by 16 EI. And deflection at center, it is WL cube divided by 48 EI. So remember, if simply supported beam with central point load W, the slope at theta A and theta B are same, and the values are WL square by 16 EI, and the deflection at A will be 0, deflection at B will be 0, but deflection at center is maximum, that is deflection at C, that is Y C is equal to this WL cube by 48 EI. So this is what the small standard cases we have considered, and we have found out slope at theta A, slope at B theta B, and deflection at C, that is YC. Okay, so I hope you understood this. Please go through once again. Okay, try to solve this derivation, because in exam such derivation, standard cases derivation will going to ask in the examination. Now in the next session we will going to consider same simply supported beam but with UDL. Okay, so thank you for attending this session. If any doubts are there, please feel free to ask me. Okay, thank you very much.